Imagine a machine so powerful that in just 1 second, it pumps enough fuel to drain a swimming pool while surviving fire, cryogenic cold, and 30,000 revolutions per minute. That's the power hidden inside SpaceX's Raptor engine. It's not just an engine, it's a network of spinning monsters called turbopumps, each delivering gigawatts of power in a fraction of a heartbeat. But how do these small, metal beasts work together without tearing themselves apart? Let's uncover how SpaceX's Raptor turbopumps push the limits of physics to launch humanity toward Mars. When you look at a Starship launch, you see thunder, light, and fury. But the real magic happens inside, where precision engineering meets absolute chaos. The Raptor engine is the heart of SpaceX's Starship and Super Heavy booster, and at its core lies a pair of turbopumps that make it all possible. Without them, the rocket simply wouldn't ignite. The job of these turbopumps is simple to explain, but nearly impossible to achieve. They take liquid methane and liquid oxygen, both stored at cryogenic temperatures, and pump them into the combustion chamber at pressures higher than those inside a tank of deep-sea submersibles. Each pump must push hundreds of kilograms of propellant every second into a chamber that burns at over 3,000 degrees Celsius.
Let's pause for a second to understand just how extreme this is. The Raptor's combustion chamber pressure is about 300 bar. That's more than 4,300 psi. To overcome that, its turbopumps must deliver propellant at even higher pressure, around 350 bar. And they have to do this with perfect timing, or the engine explodes. Each Raptor engine contains two turbopumps, one for liquid methane and one for liquid oxygen. Both are powered by small rocket engines called preburners. These preburners ignite a tiny fraction of the propellant to create extremely hot gas, which spins the turbine connected to the pump. In less than a second, the turbine ramps from 0 to over 30,000 revolutions per minute. The power generated is staggering. Each turbopump delivers more than 100 megawatts of mechanical energy. That's about the same as an entire electrical power plant, from a machine that fits inside a person's arms. Let that sink in. One Raptor engine's turbopumps generate more power than 3 nuclear submarines combined. And remember, Super Heavy carries 33 Raptors. For a few moments during launch, that means the rocket's turbopumps alone are collectively producing over 6 gigawatts of power, enough to light up a medium-sized city. Now here's where SpaceX broke new ground. The Raptor doesn't use a traditional cycle. Most rockets use what's called a gas generator cycle, where some propellant is burned to drive the turbine and the exhaust is thrown away. It's simple but wasteful. SpaceX went for something far more ambitious, the full-flow, staged combustion cycle. In this design, both propellants, methane and oxygen, go through their own preburners, producing two types of hot gas, fuel-rich gas and oxygen-rich gas. Each drives its respective turbopump turbine, and both streams later meet in the main combustion chamber where they burn completely. This means no propellant is wasted, efficiency skyrockets, and every bit of energy is used to make thrust. But this innovation didn't come easy. Running oxygen-rich gas through a turbine is like sending fire through a blender made of metal. The oxygen tries to burn everything it touches, even the steel itself. So SpaceX had to develop new alloys, coatings, and cooling systems to make the oxygen turbopump survive. The result? One of the most advanced pieces of machinery ever built. Let's talk numbers, because this is where it gets wild. Each Raptor engine produces roughly 230 tons of thrust. That's nearly 500,000 pounds of force. To achieve that, the turbopumps need to feed the engine with almost 700 kilograms of propellant every second, roughly the weight of a grand piano every second, and keep doing it for minutes at a time without missing a beat. The methane turbopump alone spins at about 30,000 RPM, while the oxygen turbopump can reach 36,000. The shaft connecting the turbine and the pump endures temperatures ranging from -183 degrees Celsius on one end to over 1,000 degrees Celsius on the other. The difference across a single spinning metal rod is over 1,000 degrees, all while it rotates faster than any car engine ever built. The bearings that support this rotation face tremendous loads. They can't use oil because it would freeze or burn. Instead, engineers rely on thin films of the propellants themselves as lubricants, a technique called hydrodynamic film lubrication. It's a microscopic balance act between flow, friction, and temperature. Too little pressure and the shaft melts. Too much and it seizes.
Even the startup sequence is a work of art. The turbopumps can't simply spin up at full speed. The Raptor engine's preburners ignite in a carefully timed choreography, ramping up pressure in milliseconds. Valves open in a pre-programmed sequence, gradually feeding gas to the turbines until they reach full speed. One wrong timing pulse, one valve lagging by even a fraction of a second, and you risk a hard start, a violent explosion inside the engine. To make sure that never happens, SpaceX runs extensive simulations and test firings. Every Raptor is instrumented with sensors that feed data to a central computer, monitoring pressure, flow rate, vibration, and temperature thousands of times per second. If an imbalance occurs, say one pump spins slightly slower or a flow sensor reads off nominal, the system adjusts throttle levels or shuts down the engine entirely in milliseconds. That's how SpaceX managed to ignite 33 Raptor engines on Super Heavy simultaneously without turning the pad into a crater. The synchronization of those turbopumps is a ballet of high-pressure fluids and computer-driven precision. But let's dig deeper into why SpaceX went through all this trouble. Raptor's turbopumps are designed not just for power, but for reusability. Traditional engines like the F1 on the Saturn V were designed for one-time use. They didn't have to survive beyond a few minutes. Raptor, on the other hand, is meant to fly hundreds of times. That means the turbopumps must endure a repeated startup and shutdown cycles, massive thermal stress, and hours of operation without degradation. To achieve that, SpaceX uses additive manufacturing, or 3D printing, to build complex turbopump components as single, seamless parts. This eliminates weak points like welds and joints. It also allows engineers to create intricate cooling channels that snake through the pump body, keeping it stable even as temperatures fluctuate wildly.
The materials themselves are custom alloys designed to resist oxidation and fatigue. The oxygen turbopump, for example, is made of high-nickel superalloys with internal coatings that prevent burning under oxygen-rich gas flow. These materials didn't exist a decade ago. SpaceX had to invent and test them in-house. All of this contributes to a key metric, thrust-to-weight ratio. Because turbopumps make up a large portion of an engine's mass, lighter pumps mean better overall performance. Despite their massive power, each Raptor turbopump weighs only a few dozen kilograms. The entire Raptor engine delivers over 230 tons of thrust while weighing around 1.6 tons, giving it one of the highest thrust-to-weight ratios of any rocket engine ever made. Let's put that into perspective. When all 33 Raptor engines fire on a super heavy booster, their combined turbopump power output exceeds 6,000 megawatts. That's more than the peak power generation of India's largest hydroelectric dam, and they achieve this in seconds. Now here's the cliffhanger. Raptor 3, the next generation version currently in testing, is pushing these limits even further. SpaceX is redesigning the turbopumps for higher efficiency, lower weight, and faster manufacturing. Early test data shows that Raptor 3's turbopumps can deliver more pressure and flow than Raptor 2, yet they're simpler and cheaper to build. That's critical for Starship's goal of rapid reuse and mass production for Mars missions. But there's another reason why Raptor's turbopumps are special: methane. Unlike kerosene or hydrogen, methane is both clean-burning and easy to handle. It leaves almost no carbon residue, which means the turbopumps don't get clogged with soot after each flight. This makes turnaround maintenance much faster, exactly what you need when you're building a fully reusable launch system.
And here's something few people realize. The turbopumps don't just deliver fuel, they help control the engine's stability. Pressure feedback loops from the pumps directly affect how the main combustion chamber burns. That's why every Raptor engine has a complex control algorithm that links the preburners, turbines, and combustion chamber in real time. SpaceX engineers sometimes describe the Raptor not as a single engine, but as a network of engines within an engine, all communicating at millisecond precision. Every flight test you see, every Starship prototype that lifts off, is a live orchestra of these turbopumps working in harmony. Even if one shows signs of vibration or overpressure, the system can automatically shut it down and compensate with others, keeping the booster stable. Now, let's talk about one of the most impressive feats in Raptor's evolution: surviving multiple ignitions. In the early days, even testing a full-flow engine like this for a few seconds without melting was an achievement. Today, SpaceX Raptors can run for several minutes, shut down, cool, and restart. Some have been fired over 20 times on the test stand. That's not just progress, that's a revolution. Each test brings SpaceX closer to its goal, a rocket engine that behaves more like a jet engine, reliable, efficient, and reusable at will. And at the heart of that dream are those turbopumps, spinning faster than your eyes can track, converting chemical energy into motion with mind-bending precision. So next time you watch a Starship launch, remember this: beneath the fire and noise are 66 turbopumps, each one generating more power than a skyscraper-sized wind turbine, all perfectly synchronized. That's what allows humanity's biggest rocket to rise from the pad, defying gravity and turning methane and oxygen into pure acceleration. That's not just engineering, that's controlled chaos turned into art. If this deep dive into the Raptor's powerhouse left you amazed, make sure to hit that like button, subscribe, and share this video with your fellow space fans. Because on this channel, Rocketry, we don't just talk about launches, we explore the heartbeats of the machines that make them possible. And in the next episode, we'll take you behind the scenes of how SpaceX plans to catch an entire super heavy booster using Mechazilla, live, midair, with millimeter precision. The future of rocketry isn't just about reaching space, it's about mastering the power that gets us there. Stay tuned and keep your eyes on the stars.